All right, let's begin. We don't have too many minutes we have a lot of contents to cover today. So let's begin. All right. If you have any question about the material today, you can just ask anytime on the chat. About the attendances, we'll actually upload the policies on Classroom after the class. So, if you have any questions about the attendances, you can please wait until then. All right, let's begin. So today we're going to talk about basic machine learning. So before we dive into deep learning, we're going to cover basics of what is a loss function, how do we learn to train a function, and how do we train a function, and how do we know how we actually did a good training, and what is an optimization, what is parameter learning, and what kind of classifiers are out there, what kind of clustering out, just very, very basic stuff. And it's actually this whole content we're going to cover today. It's going to take actually a semester or two to really learn stuff. So this is just just looking at the surface, and then we're going to have to move on, because the whole thing about the purpose of this course is actually learn how to write codes in PyTorch to build a deep learning model. So as I said, the prerequisite of this class was just, learning. If you know how to write codes in Python, that would be okay. But the better recommended prerequisite is that you took a undergrad machine learning course. So hopefully for those who took the undergrad machine learning course, this would be a recap. For those who never heard of machine learning before, or who never took a formal machine learning course, this would be your starter. So please pay attention. And then you would have to actually review what we've learned today on your own time before we move on to deep learning. All right. So as I mentioned in the introduction last week, AI and machine learning and deep learning, they're all just, there are constant one, like there's a hierarchy of they are hierarchical concepts. So on the very high level, there's AI, which is whatever effort you put into trying to make machines mimic human intelligence. And then there's subset of AI is machine learning, which is you train a machine using data. So that is statistical learning. And then within machine learning, there's deep learning, so which is among machine learning. It's still data-driven machine learning. But among machine learning, a particular practice or research that is interested in using a large number of data, like a heavy volume of data with large neural networks, that is usually what we call deep learning. So we're going to move on. And we talked about why deep learning. So there were several things about that is attractive about deep learning. One was high performance. The other was less feature engineering. So we're going to just jump that. And before we start studying deep learning, next week we're going to talk about basic machine learning stuff today. And there are three machine learning categories, largely three categories. Sometimes people exclude reinforcement learning as they don't treat reinforcement learning as a third category. Some people do. So I'll just treat them as a separate category. So there's supervised learning, there's unsupervised learning, there's reinforcement learning. In Korean, they would be 지도학습이고 비지도학습, 비지도학습, 그다음에 이제 강화학습 이렇게 되겠죠. So there are three categories. So what is supervised learning? Supervised learning is learning a function, actually, or training a function or learning a function. I guess they're interchangeable. So learning a function that maps an input X to an output Y. So you have an input and you have an output, and you want to learn a function that maps between the function. Actually, the definition of a function is that there's a function here with your domain, and then you have a function of a codomain, and there's like a function f that maps elements from X to Y, and there are certain properties that this f must satisfy in order to be called a function. Like you can't have one element being mapped to two things at the same time. Like this is not allowed. Several things, and we're basically doing this. So there's an input and there's an output. So what are the examples? Image classification is the most one of the representative examples of supervised learning, and then there's French-English translation can be seen as a supervised learning. Image captioning also supervised learning. So for image classification, you have a you have a domain of images. So it's like images. There could be a cat image. There could be a dog image. Like there, like people, car, dog. A lot of there can be actually the number of elements in the set called images is probably infinite, right? There is not a finite number of images in this world. There can be infinite number of images. So there's one domain, one set called images, which would be our X, and then there's, let's say we're doing dog or no dog classification. We're just simply doing a binary classification, whether a given image is a dog or it's not a dog. So in this Y domain, in the label domain, there are only two elements, which is dog, and another is no dog. And what you basically want to do is you want to map all your elements in your images, the domain, to the labels in Y, your codomain, or it would be an image. So and it can be only one of the two. It could be either a dog or no dog. And hopefully what we want to do is we want a function that correctly classifies or maps a image from this set correctly to the labels. There are only two labels here to this set. So we want to see a function that looks like this. Like this, like correct, it would be your correct function. Yeah. So that is one way of looking at supervised learning, especially image classification. French-English translation is the same thing. So there is a set of French sentences and there's a set of English sentences. So it would be, like I am a boy. Like, well, I don't know French, so I'm going to just write equivalent, just English here. I am a boy. You are a girl. You are a girl. Like, again, the number of elements in the French set would be infinite. There is no finite number of sentences in the world. Like you can think of imagine any sentence in your world, and it might be the first time you think of that sentence in the entire world, right? So there's it's an infinite element set, and it's the same deal with English. There's like I am a boy. So this will be, I'm going to put quotation mark to mark it as a French. And I am a boy. You are a boy. Are you a girl? There will be a lot of elements in English set as well. And hopefully what we want to do is we want to learn a function f that maps I am a boy correctly to here. And you are a girl. Well, actually, there should be a you are a girl somewhere. So you are a girl. So these are all elements. And you want to map it here. And then somewhere you want some other sentence to be mapped here and another sentence to be mapped here, something like this. So that is French-English, how you can view French-English translation as a function. Image capturing is the same deal. There's one set of images and another set of sentences, and you want to basically map between the two using a function f. Right. So far, so good, right? So there can anything that has an input and the output, it's just supervised, can be seen as supervised learning. Then what is unsupervised learning? Unsupervised learning is learning a distribution or a manifold function of data X. And note that there is no label Y. So there in supervised learning, there was X and Y. So there's a pair of set that you need to perform supervised learning. Unsupervised learning, on the other hand, you just need the data. You don't need a label. And basically, the representative examples are clustering or low rank matrix factorization or kernel density estimation. So these two, the clustering is actually trying to, if you know what clustering is, well, clustering can be seen as an effort to see the properties of the data given to you, like how many clusters or how many groups are there in your data, and to get a feel about your data. Like if you don't know the structure of the data, you can simply just run a clustering algorithm, like k-means clustering or whatever clustering algorithm you prefer, and then see the underlying structure of your data. Lower rank up matrix factorization is like if you have a feature matrix and then you want to approximate it, then you can use lower rank matrix factorization. You also here you can view like the structure of the data, like how many, like what are the eigenvalues or what are the singular values when you do lower rank matrix factorization, like, and you can approximate the number of ranks in your feature matrix. Kernel density estimation is basically, you want to estimate the density of your the probability density of your data distribution, and so you can say like, okay, so this sample, this particular, like if you have a lot of samples in your space, then, and some samples have like high density here, some have like low density here, and you can think of this as like a two-dimensional space. Then if you can do a kernel density estimation or any density estimation, then you can say that like this data, this particular sample here is like has a probability of like 0.00 some percent of being occurred in your data set, something like that. And for example, if it's in the very low probability density region, like here, then you can say that, okay, so the probability of seeing this data in your data set is, this sample in your data set is like 0.00000001%, something like that. Right. And so that was unsupervised learning. The last is reinforcement learning, which is a bit different from the other two. So reinforcement learning, given an environment E, so you need an environment, which is different from the other two. And a set of actions, A, you learn a function that maximizes the long-term reward R. So there are three components here. There's environment, set of actions, and the reward R. So there you can see that there is no data. That is the important thing. So there is no data, and there, especially compared to supervised learning, where you have X and Y. So Y would be your true label, actually. So X is your input data, input sample, and Y is the true label of those samples. Here, you don't have, in reinforcement learning, you don't have that kind of stuff. You let a machine or an agent to run around in the environment, to play around in the environment with the set of actions A, and then the agent will eventually obtain a reward R, could be high, could be low, depending on the parameters of the agent. And then based on the reward, you want to tune or you want to learn a function that maximizes the reward in the end. So the examples are Go. So everybody knows the AlphaGo challenge. So in Go, the environment would be the Go board. 바둑판이 되겠죠. 바둑판이 되고 Go board, and the set of actions that are allowed to play in the Go board would be, placing your stone. If you're like on the black side, then you're placing your black stone in one of the 19 by 19 grid on the Go board. So that would be your set of actions, and then the reward would be whether you lose or win in the end. So that would be a very long delayed reward, because you have to, the only way to get a reward is to play the entire game throughout, then you get a reward. So that is like a very long horizon reward. So Go, Atari game, also Atari, everybody knows Atari game, how the machines can play the computer games, like Atari, StarCraft, Dota, they play a lot of games these days. Atari was, so the Atari game itself would be an environment, and then set of actions would be your joystick and like button A and B, and then you get a score. So the scores are immediate, actually, compared to Go. You can see when you play like a space invader, you can destroy the enemy ships, enemy airplane, and then the score goes up. So that would be a bit more immediate reward. So it's a bit different from Go. Self-driving car as well, like being on the road would be your environment, and then turning your wheels, turning your handle, and stepping on the gas and brake would be your set of actions, and the reward would be whether you got to the destination without any accident or not, something like that. So the important thing is that here, actually, before we move on, so especially these days, the lines are a bit blurry between these two when it comes to generative models instead of self-supervised learning. Like if you think about BERT, the labels come from the data. So usually in supervised learning, labels come from human annotation. Like people have to annotate whether something is a dog or not, something is a cat or not. whether something is like a car or not. Like people have to look at the samples and then annotate it and like hand label it basically. But in BERT, if you're familiar with BERT, if you're not familiar with BERT, that is okay. We're gonna learn BERT anyway. So in BERT, when you prepare a training sample, you don't have like people don't have to manually label it. You just remove certain part of the sentence, certain words in the sentence, and you force the machine to predict it, right? So in that case, it could be seen as an unsupervised learning, but some sense it is still supervised learning because there's X and Y at the same time. Generative models are also a bit somewhere in between because generative models, you can view them as basically learning a probability density of your data set, but then you still need an output. You still train your generative model with, if you're using GAN, you need like a discriminator output. If you're training VAE, you still need a reconstruction loss, something like that. So the lines are a bit blurry. In this class, in this course, we're going to focus only on these two, supervised learning, unsupervised learning. And we're not going to do actually clustering, but when I say we're focusing on unsupervised learning, we mean generative models and pre-trained models. And we don't handle reinforcement learning in this course. But if you're interested in reinforcement learning, there's a separate course provided by our department. So please attend that instead. All right, so far, any question? 네, 질문 없으시죠? Right. And then moving on. So a little bit of a introductory description of optimization. So all these like supervised learning, unsupervised learning, reinforcement learning, it's all learning, right? So there's a reason that they're all like the word learning is in there. So what do we learn? We learn a function, as I said. We learn if it's for supervised learning, we learn a function that maps between X and Y. If it's unsupervised learning, we learn a function that estimates the probability density or estimates the structure of the data, something like that. So, and yeah, how we learn or how we train a function is we use data. So that is why it's called statistical machine learning. Like for example, you can come up with a function that maps between X and Y without data. It's just purely driven by human knowledge, which would be like expert systems back in the 70s or 80s, So, but here we rely on data, and especially, for example, in supervised learning, we rely on labeled data that has X and Y, and then we use that to train a model. So how to train your model? So how to train? We need, even in order to obtain a good model, good function, we need to train it because it doesn't show good performance from the start, right? So how to train your model? So your model consists of fx semicolon theta here. X is your input, so X is given to you because you already have. We're assuming that we're already given the data. If it's supervised learning, it's data of X and Y. If it's unsupervised learning, it's just data X. And your model would have a set of parameters. Theta could be a number of parameters. It could be one parameter, but we're just going to call it theta. So in order to train your model, it means you're adjusting your theta, which is responsible for the behavior, like how your function or how your model behaves, right? So we want to obtain a good parameter so that your model works, so that your model behaves as intended. And in order to do that, in order to train, you need to have a goal. So because without the goal, how are you going to train your model anyway? So we call this goal a objective function. So we are basically what optimization is training your model's parameters to achieve your goal, which is called objective function. So for example, if we're doing again binary classification, given an image, classify whether it is a dog or it's not a dog. So it's a dog or no dog. In this scenario, in this binary classification scenario, the objective is obviously correctly classify dog or no dog given an image. And in the same sense, we call that achieving an objective function is sometimes called minimizing a loss function. So loss is in Korean 손실이죠, 손실. 그러니까 이제 손실을 줄이는 건데. So the reason that it's called loss function is that loss is incurred. So your model is experiencing a loss when it misclassifies an image into one of the two categories, dog or no dog. If it misclassifies, loss incurs. So loss happens, basically. And if it correctly classifies, there is no loss. So what we want to do is we want to minimize the loss. 그러니까 손실을 줄이고 싶은 거죠. 이 개인데 개가 아니라고 분류를 했거나, 아니면 뭐 개가 아닌데 뭐 고양인데 개라고 분류했으면 이제 손실이 발생을 하기 때문에 이제 이거를 loss function, 손실 함수라고 부르는 겁니다. And 그걸 당연히 이제 우리는 손실을 줄이고 싶겠죠. 손실을 줄이는 함수가 좋은 모델이 되겠죠. So whatever function or model you have, the model that minimizes the loss would be a good function. So that is our objective. Yeah, and the loss function usually consists of only two things: true class and predicted class. So we're talking in the context of supervised learning. So in those cases, loss consists of two elements. One is true class, which is given to you, because your data needs to have x and y, true y. So that y would be here. And then y prime, which is predicted class. So y prime comes from your model. So your model has an input x given to you again. So this x goes to this model. And then based on the input and the parameter, that your model would output a predicted class y prime. And then we compare these two. Basically, what we do is we compare between the true and the predicted y prime, and then see if there's any loss. Right. Sometimes the loss function is called also a cost function. 이제 비용 함수라고 하기도 하죠. In the strictly optimization sense, from industrial engineering, 그 산공과나 이런 데서 하는 이제 옵티마이즈 최적화 같은 데서는 당연히 비용을 줄이는 게 목적이잖아요. 뭘 제조하는데 뭐 돈이 얼마 든다거나 아니면 뭐 재료가 얼마 든다거나 이런 게 다 이제 비용이잖아요. 그러니까 비용을 줄이는 일을 하고 싶은 것도 이제 최적화기 때문에 이제 이거를 그 비용, cost라고 하거나 뭐 loss라고 하거나 이렇게 이제 interchangeable하게 본다 이렇게 보시면 되겠습니다. All right, moving on. So the loss function, the most representative, one of the representative loss functions that we are familiar with is here is binary cross entropy. We call it binary cross entropy, BCE. So we use binary cross entropy loss or binary cross entropy function as a loss function for for training a binary classification function. And we'll get into the detail of why this makes sense. Probably next class. But you can see intuitively what happens is that know that y can either be 0 or 1 because we're doing a binary classification, and consequently y prime can be any value between 0 and 1. It could be 0.1, it could be 0.3, it could be 0.99, it could be any value, but your label is either 0 or 1, right? So if your label is 1, then this term goes away, because of here, and you're only left with this. And then you want your y prime to be as close to 1 as possible, so that the loss is minimized. If you get rid of this negative sign away, then what you're doing is you're maximizing you want your y prime to be as close to 1 as possible. And if your true y was 0 instead, if it was 0, then this term would go away, and then you're left with this term, and this term would be 1 because y is 0. Then what you want your y prime to be is as close as possible to 0 in this case. So it's basically you're telling your model to mimic y, the true label, so that your predicted label y prime could be the same value as y. So that is what binary cross entropy is. And so this binary cross entropy function, BC, is a typical loss function used for training a model to perform binary classification. But there are other loss functions as well. I guess that's here. Okay, so before we go into the other loss functions, so what we need to do is you need to find theta parameter that minimizes the loss, as I said, because there's true label here, then your predicted label y prime, and your predictable label y prime is determined by the parameter of the function. So what you can only do is that just meddle with theta. You can't touch y or you can't touch x because they're given to you as data. All you can do is play with theta so that the output y prime is as close as possible to y. And that is what we call a optimization. And as I said, there are other loss functions besides binary cross entropy loss. For example, if you're doing regression, then the typical loss functions that you use is like MSE, mean squared error, or mean absolute error. So your loss function, you need to use the right loss function to perform your task. If it's a regression task, you can use MSE. If it's binary cross entropy, if it's binary classification, you can use BCE. If it's multi-class classification, you can still use negative log likelihoods, yada, yada, yada. All right. Moving on. So how to optimize here. So far it was just a high level concept. You have data X and Y, and you have a function that is governed by the parameter theta. And what you want to do is you want to define a loss function, and you want to minimize it in order to achieve your goal. And minimize the only way to minimize it is optimally adjust your parameter theta or model parameter theta. So that was just high level concept. So how do we do it? How do we actually optimize the parameter theta? So we start with a very, very simple example. Let's assume that your model f is just a quadratic function. It's x squared negative 2x. Let's assume that your loss function is just this. So you want to minimize your function f, which can be seen as your loss function for now. And it happens to be a quadratic function, x squared minus 2x plus 1. And you want to minimize it. And how do we minimize it? If you think about what you learned in high school, 이제 극소점, 극대점 이런 거 다 배웠었잖아요. Or actually, if you just remember what you did in your undergrad calculus or forgot math for engineering. You can just readily just know that you can there's an analytical solution. Like that x equals 1 gives you the lowest point of this function fx, because x negative x squared minus 2x plus 1. What does it look like? It looks like this. So there's 1 here, there's 1 here, and then your function would look like this, right? It's not a perfect drawing. So this is your fx, and the lowest point, which is basically the minimum point, is right here, right? So you want to, and here the parameter is actually your parameter is x here. So you want to choose the x that minimizes your function fx, and that x happens to be 1, x equals 1 right here. And so you can analytically solve it. And actually there's a guarantee that there's only one minimum point in the entire, in the entire codomain or in the entire output range. And why is that? How do we know that there's only one global minimum? Before we even start looking for the answer x equals 1, we immediately just know by looking at the fx, this form here, we already know that there's only one global minimum. One global minimum, meaning there's only one minimum point in throughout the entire range of fx output. The reason is, any takers? 네, 왜 너무 쉬워서 대답을 안 하시는 걸로 생각을 하겠습니다. 당연히 이제 그 2차 함수니까 미니멈이 하나밖에 없는 거겠죠. So it's because it's a quadratic function. That's why there's only one global minimum. If it was, like a fourth order function, actually, let's go with the third order function. If it was a third order polynomial, then it would look like this. If it was fourth order, if like fx equals x to the third plus something, and if it was fourth order, it would look like this. Wait, is it true? Yeah, fourth order would look like this. Fx equals x to the fourth plus yada yada yada. In this case, here, in the third order case, there's actually more than just there's. I mean, well, there should be there's one global minimum somewhere down here, but it would be a negative infinity. So that's kind of like that doesn't help our point. If we were to deal with fourth order polynomial function, then there are two minimum points, right? There are two minimum points, and we have to decide, and we will have to actually see which one is lower, because if we assume that this is our loss function, if this was our loss function, then we want to choose the minimum point as small as possible, because minimizing your loss is basically training your model, right? So we want to choose the minimum point out in this entire region. Like there's like an infinite number of points that you can choose for your model parameter, and we want to choose probably this one because this is lower than this guy. So based on your loss function, you would have to choose very carefully your model parameter. Question: what happens if you have multiple minimums of the same value? Well, actually, that rarely or probably never happens. But in that case, it's probably okay whether you choose one or the other, because they have the same loss value. But it's probably never ever happens. Like for two values, for the two real values to be exactly the same, that would be unrealistic. Hopefully that answers your question. 그러니까 실수값 두 개가 정확하게 똑같다는 거가 이제 현실적이지 않죠. Right, so that was an easy case. So if your loss function was as simple as this, then you can just readily solve it by analytically just deriving a like a factorized form. But in reality, your loss function is not as easy as this guy. Your loss function is actually way more complex. Not meaning imaginary, just 더 복잡하다는 거죠. It's just more complicated. And it is typically a non-convex function. Convex function이 convex라는 게 이제 이렇게 볼록하게 생긴 걸 이제 convex라고 하잖아요, 주로. 이렇게 생긴 것도 convex이긴 한데 어쨌든 간에. So it's a non-convex function, meaning that there can be more than one minimum point, or we call that local minima. So, for example, in the previous case, there are two. Oops, right? I accidentally erased it. There are two minimas. There's 1 and 2, and this guy is these two are both called local minima, and this guy is a true minimum, so it's called global minimum. So it's typically our loss function is complicated, and it's a non-convex function, so there can be many local minima, and usually there's no analytical solution. Analytical solution 이제 손으로 이렇게 막 종이나 풀어가지고 이렇게 100% 정답 딱 내고 그런 거 이제 analytical solution인데, 근데 이제 그런 걸 할 수가 없다. 그러니까 이제 뭐 미분 보통은 이제 the way you usually, if you remember, obtaining the lowest point in your function in high school senses, you simply just do a derivation, you do a differentiation, and then you set your derivative to 0, and then you obtain the value that sets your derivative to 0. I mean, the x that sets your derivative to 0. So that is how you obtain analytically obtain your minimum point. But in reality, with loss function as complex as your typical loss functions like MSE or like binary cross entropy, there is no analytical solution. So you have to approximate it numerically. So you need to look for a numerical method, right? So we're going to talk about how to do it. So numerical method. Numerical method is whichever effort that you use to iteratively find the better parameter until you're satisfied. So you start somewhere. So we have we have gradient descent, but in a more high level concept. For example, let's say that your loss function. This is your loss function. Well, this is your loss value, and let's say that your loss function looks like this. Something like that. And this is your theta. So let's assume that for the sake of argument, let's just assume that your loss function is controlled by just one variable. It's a univariate function, one univariate function with one variable theta. Theta is a scalar value in this case. And what you want to do is you want to find this particular point, this particular theta. So theta, this is your theta prime. This is your ideal theta because it sets your loss. Because at that point your loss is minimized, right? So far so good. But you don't. If there is no analytical solution, then you have to resort to numerical method. And typically, with numerical method, you just pick anywhere in your theta. There can be, from negative infinity to the positive infinity. You just pick any theta anywhere, and let's assume that you happen to pick here. So this is your. I'm going to erase this small theta here. This was your theta zero. So you just picked here, and then what you do is you typically rely on the gradient information to look for the minimum points. So here the gradient is this. So you go down the gradient. You go the gradient. 그러니까 이제 이 뭐라 그러지 이거를 그 그레디언트가 한국말로 뭔지 모르겠네. 이제 경사를 따라가는 거죠. 이제 그 경사 추적법이라고 그러면 그레디언트는 경사강법이라고 하던가 이제 그러는데, 그러니까 이제 이 경사 슬로프를 따라서 이제 그 방향을 쭉쭉쭉 내려가는 거를 이제 그 for loop을 돌려가면서 하는 게 이제 iterative methodism. So you go down the slope because you want to go down the slope because you want to find the minimum point in your loss function, your loss geography, loss surface. So you go down the slope, maybe a little. You go down here. And then this would be your theta 1, and then you go down again, and then this will be your theta 2, and so on and so forth. You go down, until you're here, which is your theta prime, theta star. And you don't want to go down too much. You want to go down in a very small step. If you go down this direction, which is your gradient, too much, then you will go all the way here, which would be overshooting, and then your theta would be theta 1 would be here, which is actually you've missed your minimum point. So you want to go down in a very small steps, like small steps like this. Right. So that is numerical method. And the problem with the numerical method is that the problem that when you don't have an analytical solution is that your solution depends on your initial point. For example, here we happen to choose the good initial point theta 0, which was here, so that you can go all the way down and then just go to the global minimum at once. But if your theta 0 started here, for example, if this was your theta 0, then you would start here and then go down the slope in this direction, like here, and then you would reach here, and then that would be your local minimum, and then you would be done. So you know that the gradient here would be 0. The gradient at the minimum points are usually they're like 0, right? So you know that you've reached the minimum point around the neighborhood, and you can't. Well, you don't want to go past it because you don't know what's out there. Like if you've reached here, your theta hat, then you know that your gradient is 0, and then you know that you're at the local minimum, and then you don't want to go adventure. You don't know what's really out there. It could go that, it could go like this, it could go like this. You have no idea until you actually reach there, because it's such a complex non-convex function. So you're satisfied here, and that would be your solution. And you know that, in the global sense, that is not the optimal solution, because the optimal solution is here, and you're satisfied with the local solution here. And that is just because you chose, accidentally, you happen to choose a suboptimal initial point, right? So that is the whole concept behind the numerical method in a high dimension, in a non-convex function. Any questions so far? Yeah, that's a good question, because here it should have been f theta. Like this. Your loss function would x in the quadratic function example. If we wanted to see that as a loss function, then x should have been a theta. And there is no and the input would be, there is no input actually. It's just a very simple example to let you know that the quadratic function has only one global minimum and an analytical solution. Question from Kim Ji-young. Actually, that's a direct message, but it's a good question. So I'm just gonna share it with everybody. So the question is, how do we know if we've run into a local minimum or not? Like if we obtain the solution, do we know that it's a local minimum or not? And I would say generally no, because in order to know that you've reached a local minimum or global minimum, in order to know that, you would have to have a global view of your loss landscape, your loss function, like how your loss function looks like in the entire scenery, in the entire space. And usually you can't do that because the loss functions that we typically deal with in deep learning has how many dimensions? Like 1 billion dimensions, like 1 million. Like this example here is a one-dimensional loss surface because we only have the scalar value theta that controls our loss. But in typical deep learning with like, GPT-3s and BERTs and all that, there are billion or 100 billion, 그러니까 이제 1억, 10억, 100억, 1000억 개의 변수가 로스를 컨트롤한단 말이에요. 지금 여기서는 한 개의 변수가 로스를 컨트롤했잖아. 근데 이제 딥러닝에서는 10억 개, 100억 개, 1000억 개의 변수들이 이제 로스에 관여를 하기 때문에 그 그림을 어떻게 그리나요? 그림을 그릴 수가 없고 뭐 상상할 수도 없고 그걸 다 어프로크시메이션 할 수도 없습니다. 그래서 보통은 모른다. So yeah, there's no way of really knowing it. But so people have actually wondered about. A lot of people have done a research about this local minimum problem in deep learning. Like when we do stochastic gradient descent to train your deep learning model, how do we really know that it reached the good solution? Because you know that numerical methods are affected by initial points. So how many times do you have to train your model to really believe or safely guarantee that your model has learned at least a reasonably good local minimum? Like how do we know that? So people have done research on that, and so there were some findings back in the 2015, 2016, I guess, maybe back or 2014, like several years ago, that deep learning models loss surface actually has a lot of local minima that has like similar values. So this answer leads back to Joshua Yedam's question, like what happens if you have multiple minimums of the same value? It's similar things happen in deep learning. Like deep learning models have such a very, very like large number of local minimums that are not same value, but like similar values. Like, so you can choose whichever loss you want. Well, I mean, whether you land here, whether your parameter lands here, doesn't really matter because they all like provide like similar loss value anyway. So that is like, but that's still like, it's like a conjecture. Like nobody can really know, but it's just a suspicion that maybe deep learning models loss surface looks like a very well-tamed loss surface like this, like a lot of local minimums that have the similar values. So whether you start here, theta 0, whether you start here, whether you start here, it doesn't really matter because you would get to any loss like local minima that has like reasonably good solution. Right. And these days, a lot of people, still a lot of people focus on how obtaining a good loss surface so that your parameter doesn't get into like a very weird space or weird ridges or weird valleys, So it's a very complex field of research. Like depending on how for example, if you connect your model with a residual connection or not, that already tweaks your loss surface. For example, let's say that your loss surface looked like, how do I do this? Like if your loss surface looked like this, then that would be very squiggly and it would be very hard to train because it has a very like sharp angles, and you won't be able to get out of it or get into it. Like you would miss it. Like sharp edges if you have sharp edges in your loss surface, it's not a good sign. But for example, if you add like a couple of residual connections in your model, then your loss surface would suddenly turn into like a very smooth function like this. Like, so it all depends on what kind of model you use. Actually, the loss surface is determined by the loss function that you use, like whether you use like MSE, mean squared error, or whether you use mean absolute error. That also changes your loss surface. But another large factor that changes your loss surface is the architecture of your model, actually. Like whether you're using ResNet, whether you're using Inception, AlexNet, VGGNet, like they all have different loss surfaces. And you want to develop a model that has a smooth loss surface. I mean, you wouldn't know it beforehand, but if you do it if you do research in deep learning long enough, you kind of develop an intuition. Right. All right, so I'll move on. Right, just another view of what gradient descent is. So gradient descent. So what we did here, what we did here is gradient descent basically, because we take a very small step towards the final solution, according to your gradient information, your slope information, right? So here, what you can see, this is a concentric circle. 그러니까 이거를 이제 그 등고선이라고 보시면 되는데. So actually, if you view it in a three-dimensional space, it would look like this. So this point here is here. This circle is here. This circle is here, something like this. So this is your loss function. And now it's three-dimensional. Now there's theta 1. There are two parameters. There's theta 2, and then this would be your loss. And then you want to tune your theta. So you want to find your set of theta 1 and theta 2 pair in order to minimize your loss, which would be obviously here. So that would be like somewhere here and here. So theta 2 star and theta 1 star, theta 1 star. And the way you do it is you start somewhere. For example, you start somewhere. So this would be like way high up here. You start somewhere here, and then you go down the slope, go down the slope, go down the slope, go down the slope, so like all the way down to here. So this would be your first set of theta, second set of theta, third set of theta, fourth, fifth, and so on and so forth. So you're going down to the loss surface. And your typical gradient descent algorithm or function or update algorithm looks like this. So you have your current theta, which is your kth iteration, and you have your next theta. So what you have to go on is your current theta, and then your gradient information, your gradient. And gradient information is based on your loss. So you have a loss of x. So loss consists of y and your y prime here. So this will be your y prime. You have y, true y prime, and then you have a loss function, and then you differentiate your loss function with respect to your theta in order to get the slope information. And then, as I said, you don't want to go past your loss, your minimum. You don't want to go past your solution. So you want to take a very small baby steps towards it. So this controls your baby step. How small your steps would be. That would be your eta. Eta? Is it eta? Yeah. And then you take a minus because you wanna go down the slope. You don't want to go up the slope. So you take a negative so that you can go down the slope. And then you update your current set of theta with your slope information in order to obtain your next set of theta. Then you repeat this over and over and over again until your until your gradient value becomes close to 0, or you've reached a certain loss value, or you reach certain performance metric like accuracy or AURC, something like that. All right, so that was gradient descent. And then typically in deep learning, you use a stochastic gradient descent instead. So SGD. And in gradient descent, this Y, so I'm going to erase all this. In gradient descent, what actually happens is that you need the entire X and Y in order to get the averaged gradient. You obtain a gradient from y1, comma fx1, theta. Oops, what is this? I'm sorry. I think there was a call. Sorry about that. Right. So as I was saying, you have y1, x1 pair, the first sample, and theta k, and then this would be your gradient number 1. So this would be great. Another gradient would be loss y2, fx2, theta k. yada yada. Like there you'll be like if you have like 1,000 samples, and you would have 1,000 gradients, and then you have to average them all, get the average gradient, and that would be this. This would be your average gradient across the entire samples in your entire data in your training set. Then you use that average gradient to take a step towards the next set of theta. But in a stochastic gradient descent, you don't do that anymore. You actually use a subset of your training samples to calculate the average value. So basically, what you're doing is approximation, going through the entire samples to get the average gradient would be the true gradient. I mean, it's still subset. It's still approximation because you don't know true. Anyway, let's say that this is true gradient. And then what you're doing here in the stochastic gradient descent is you're approximating that true gradient with only a subset of x's and y's. Like maybe you're using only 10 samples to get the 10 gradients, and then you average them, and then you just treat it as entire gradient average. And the reason you do that in stochastic gradient descent is because your training data is typically too big. It doesn't fit into your memory. You can't go through the entire like million, trillion samples and then calculate the gradients and then store them. And then, it's just takes too many times. It takes too much time. It takes too much memory space. It's just infeasible. So in modern deep learning, you typically use stochastic gradient descent. And actually, the true stochastic gradient descent is using only one sample at a time. You use only one sample gradient, and then you update your parameter. So that would be the true stochastic gradient. But in deep learning, modern deep learning, you use a mini batch gradient descent. So instead of using one, you use maybe 64 samples, 128 samples, maybe 256 samples, something like that. So that would be your mini batch gradient descent. And if your mini batches are sampled IID, independently and identically distributed from your training samples, then there's a theoretical guarantee that your SGD, so that your solution, your parameter obtained by SGD will be the same as the solution, the parameter obtained from gradient descent. So that is why we can safely just use SGD whenever we want, as long as your mini batches are IID sample. And yeah, modern deep learning is founded on SGD. Right. So far, so good. Any question? No. Hopefully that's a good sign. I mean, the gradient descent algorithm itself is pretty easy, but these days people like use like Adam W, like Ada Gred, whatever, like partial second order optimization algorithms. And I don't think we'll get into that. What does IID mean? IID means independently identically distributed. If I'm not sure if it's correct. 그러니까 이제 IID가 한다는 게 이제 그 트레이닝 샘플이 크게 이거를 지우고, 그러니까 이제 트레이닝 샘플이 이렇게 있고 이렇게 점들이 많이 있을 거잖아요. This is your training samples, and the way if you sample your mini batch randomly, like you take this one, you take this one, you take this one, take this one, and then you have a mini batch of 4 samples, and then your next mini batch should also be randomly chosen. 4 samples here. That is how you sample your mini batch in an IID fashion. Basically, you're choosing randomly, like truly randomly. Why the mini batch number is powers of 2? I think that's. I don't think there's any theoretical reason why. It's just that when we do hyperparameter search, actually. There is a good there used to be a good reason why, because I think if you use like TPUs in Google, I think it's more favorable that your number of mini batches are on the order of the like power of 2, like in order to maximize the efficiency of the TPU. That knowledge is like 4 years ago or 5 years ago. I'm not sure if it's the same still these days. But now it's just standard practice. Just people just increase the mini batch value by like the power of 2. It's like 32, 64, 128, 256, 512, 512, 1024. Question from Tang Huiji. Why can mini batch help avoid Suboptimal minimum. Actually, this is a conjecture. Sometimes smaller mini batch helps avoid a suboptimal minimum. So this is a conjecture. It's not like a theoretically proven. But for example, as I said, your loss surface changes by your loss function and your model architecture, but it also changes when you switch from GD to SGD because your loss surface change because your loss surface changes by when changes from when you use the entire training set to calculate the loss surface, and when you use only a subset of your training samples to calculate the loss surface. For example, if your true loss surface, like when you are using GD, let's say that your true loss surface looked like this, and you happen to start here, your theta 0. But if your loss surface changes, when you use a subset of your samples to calculate the loss surface, maybe it happens to be like this instead. Then if you even if you start here, you can still go towards here. You know? So it's just but it's like a conjecture. It could happen. Maybe it happens, maybe it doesn't happen. But basically what you're doing is you're perturbing you're like slightly tweaking your loss surfaces like in a small amount and it changes by mini batch for mini batch. When you take mini batch, like first mini batch, your loss surface looks like this. If you take your second mini batch, maybe it looks like this. Maybe in your third mini batch, it looks like this. Your loss surface changes one mini batch by mini batch, and then you're perturbing your loss surface. And when you run your optimization long enough, you hope that your parameters will go find the optimal parameters like position. Hope that makes sense. 그러니까 이제 한글로 하면은 그 로스 함수의 꼴이 이 형태가 이제 미니 배치 돌릴 때마다 조금씩 바뀐단 말이에요. 그러니까 이제 전체 트레이닝셋을 사용할 때는 당연히 이제 로스 함수가 이제 물론 파라미터 업데이트하기 전에는 이제 고정일 텐데 이렇게 딱 이제 뭔가 이렇게 있을 텐데 전체 트레이닝셋 다 써가지고 로스를 계산했을 때는 근데 그게 아니라 뭐 이런 32개만 쓴다, 64개만 쓴다. 그러면 이제 로스 당연히 이 형태가 바뀔 거고 그게 이제 어쩌면은 최적화, 그러니까 옵티마이제이션에 있어서 도움이 될 수도 있다. 이런 어떤 컨젝처가 있다. 그런 얘기입니다. 요즘도 근데 이제 그게 해당되는지는 잘 모르겠습니다. 이건 이제 다 뭐 2016년, 17년, 15년 뭐 그때쯤에 사람들이 했던 그런 생각들을 해가지고 요즘은 데이터셋이 워낙 많기 때문에 이런 것들이 이제 적용되지 않을 수도 있죠. 인터넷에 있는 모든 데이터를 다 긁어다가 이제 학습을 하면은 이런 것들이 크게 의미가 크게 별로 없어지는 시점이 오게 됩니다. 왜냐면은 사실상 우리가 사용한 트레이닝셋이 파퓰레이션 데이터라고 이제 볼 수도 있는 상황이기 때문에 이제 샘플 데이터, 파퓰레이션 데이터 있죠. 스태티스틱스에서. 근데 이제 요즘 뭐 예를 들어서 뭐 GPT-3 같은 경우는 인터넷 전체를 가지고 다 긁어서 학습을 하니까 사실상 파퓰레이션 데이터를 가지고 학습하는 게 아니냐라고 볼 수 있고 그렇게 되면은 이제 이런 것들이 이렇게 막 크게 의미가 없어질 수도 있습니다. Alright, moving on. So this is all about training your model or optimizing the model parameter. And now we're moving on to evaluation. So evaluating your model parameter, like how do we know that you've learned a good parameter or good function? And how do you know when to stop? Basically, how do you know when to stop your iterative optimization, the numerical optimization process? So you can't optimize your model forever. You can't run your for loops forever until you reach sooner or later. For example, let's say your loss looks like this, and then you start here, theta 0, and then by the time you get around here or here, which is very, very close to the global minimum, your gradient would be close to 0. Your gradient would be like this. So your gradient would be close to 0, and then your update depends on the gradient. And if your gradient is close to 0, then there would be virtually no update. Like it would be a very, very small update only. So your parameter doesn't change by that much. So sooner or later, you're going to have to stop anyway. So how do you know when to stop SGD then? And using the values, you can, as I said, you can see when your parameter changes not by much, then you know that you're at the local minimum. But you can also rely on the gradients, but you can also rely on the loss function. There are a lot of different like heuristics to estimate that you've reached local minimum, but they are not all very intuitive. Like for example, you can see your loss, you can use your loss function to see like loss value to see that you've reached a like a local minimum, but then it's not very intuitive. Like as it says here, it's not very intuitive. Like how do you know when to stop? Like if your loss value is like I want 10 to the -3 or 10 to the -4, like when are you satisfied? So usually what we do is we use another set of performance metrics, such as like things here. Like as you train your model or as you optimize your model parameters, from time to time, like maybe every one epoch, or maybe every 100 iterations, or maybe every 1,000 iterations, you calculate the model's performance by either using accuracy or ARC, precision recall blue, like these. Like you can calculate the performance, whichever metric you prefer, or whichever metric is suitable for your task, and then you calculate it every once in a while, and then see whether you've reached a satisfactory point. Like if your accuracy reaches like 95%, then you know that if it's reached a pretty good point. If ARC also reaches like 90%, it's a pretty good point, something like that. So you can use like a side information to decide when to stop. So I'm not going to go into detail what these are. You can, hopefully a lot of people really are familiar with this. Accuracy usually used for any classification tasks, especially multi-class classification. ARC used for binary classification, because sometimes your binary classification task consists of imbalanced classes. Like if your positive cases are very small compared to your negative cases, good idea to use ARC instead of accuracy. Precision recall used for information retrieval, or these days they're used in a lot of different places. Like blue score is usually used for machine translation, perplexity used for language modeling, FID score used for image generation. There are a lot of different metrics for each task in this research domain, and you have to choose the right one to properly evaluate your function. Right, and now we move on to train, validate, and test. So when you have the entire data set, you typically want to split your data set into 3 subsets: training set, validation set, and test set. And training set is obviously you use it for training your model or optimizing your parameters using SGD. Validation set, sometimes it's called development set, is a set that you use to know when to stop training your model. This is usually applicable to deep learning models. Like classical models like logistic regression or SVMs or random forest decision trees, they like sometimes some of them don't even need validation sets. But in deep learning, you typically need a validation set to know when to stop your optimization process. So you use this set to evaluate your model and decide when to stop training. So for example, like we're going to go into the overfitting, underfitting concept probably in the next slide. So this is used for validation set is used for prevent your model from overfitting. Test set is the set that is unseen during training. So you should never ever use test set during your training phase or your optimization process. You only use it once you've finalized your model by using training and validation sets. You finalize your parameter, and then you see whether it generalizes to an unseen test set at the very end. So that is how you get the test performance. All right. And n-fold cross-validation. Cross-validation is a very it has been like an essential concept in classical machine learning and even early deep learning researchers. But nowadays, I would say not so much. You'll see why. So n-fold cross-validation. So testing your model's performance in diverse train validation test splits. So here we talked about splitting your data set into 3 subsets, but you can actually do it multiple times. For example, here, if we're doing an 8-fold cross-validation, then you first divide your entire data set into 8 segments, 1, 2, 3, 4, 5, 6, 7, 8 segments. And then in the first run, you set your first subset as a test set, and then you use the other 7 as a training set. And then you do the whole thing, like training and then testing. Then on the next phase, you use in the next phase, in the next run, this becomes your test set, and then the other seven, like here, how do I draw this? The other seven becomes your training set, and then you do the training and testing again. So what basically this the benefit of this is that you get to train, you get to have multiple test sets, and this is especially helpful when you have a very small data set to begin with. Like if your entire data set consists of only like 1,000 samples, that is a not very large sample. And if you split your 1,000 samples only once into train, validate, and test, then maybe your test set consists of very tricky, very hard samples, or maybe very easy samples, so that your final test performance is not really not very insightful, or is not very useful. Because if your test samples happen to consist of only easy samples, then you would be too optimistic about your test performance. If your test samples consist of only very hard sample, very difficult samples, then you would be very pessimistic about your test performance. And it basically it's luck, you know. So like exactly like it says here, like maybe you got lucky, maybe you got unlucky with a easy split. So that is why when you have a small data set to begin with, it is a good idea to do it in a multiple fold cross validation, like at least 5-fold or maybe 10-fold if you want to get really crazy. Then you would have a multiple chance of testing your model to an unseen test set. Then you have a much more reliable estimation of your model performance. So this is, you know, basically, you know, you are increasing the number of samples to estimate your model performance. And as you increase the number of samples, the variance is lowered. I mean, this is all in basic statistics theory. Right. So that is exactly why modern deep learning really don't care that much about in-fold cross-validation, because modern deep learning, they use such a humongous, gigantic data set. As I said, GPT-3 uses the entire internet's English text. So in that case, you don't really need an n-fold cross-validation. I mean, it would be even hard to do n-fold cross-validation. If you, for example, here, if you're doing 8-fold cross-validation, it means that you need to train your model 8 times and test it 8 times. But if you're using such a gigantic data set to begin with, then you don't want to train your model like n times, because it just takes too much time and too much resources, too much electricity bill, right? So in modern deep learning, it's just time consuming and statistically unnecessary. The reason that we do n-fold cross-validation is because we can't rely on the validity or effectiveness of the test set, because your data set is too small. But if your data set is really, really big, then you can be pretty sure, confident about your test set being a representative test set. Right. Moving on. So overfitting, underfitting. Actually, I think we're kind of running out of time. So overfitting, underfitting, very important concept. So this is actually like a trade-off between data complexity and model capacity. So for example, let's say that your true data is governed by this fourth order function. So your true function is this orange line, and then you sample with some noise the samples based on this true distribution, true orange function, and then you're trying to regress, you're trying to fit your model to these samples. And let's say that you use a single, like degree 1, it's just a first order polynomial function. So this function here is like probably f x equals like ax plus b, and or actually to be more consistent with our input, theta 1x plus theta 0. So you have only 2 parameters to use, and in order to minimize your loss, and loss would be typically the distance between the samples and your function. Like the sum of all these distances would be your loss basically. And the loss will be really, really high. Actually, the MSE, the mean squared error, is 4 to the power of -1. So it's a pretty high loss. But if you use just the right amount of power, for example, if you set your fx to be theta 5 x4, x to the 4, theta 4 to the x to the 3, all the way to theta 1, x to the 0. Actually, I should have started with theta 4. Anyway, so x0. If if you increase the power of your model, power of your function, then it can properly fit the given distribution, given training set. So now that this sum of distance between your samples and your model would be much lower, and specifically it's 4 to the power of -2. So an order of magnitude has been decreased because you use the right amount of power. By the way, this is test performance. But if you use too great a power for your model, if you increase your model to the 15th order polynomial function, so your fx consists of like theta 16 x to the 15th power all the way down to theta 1 x 0, then you have too much power at hand, and your model can just exactly fit the training samples. You can see that's all the squiggly lines, you know, it's trying to hit all the samples to the perfect degree so that there's like 0% MSE loss while you're training. And that would obviously be a very unwise thing to do, because the true distribution, true function, the orange function looks like this, but now your blue function is just doing all crazy things. And now the test performance is 1 to the power of 8, which is just crazy. It's just too much loss. Like the loss has increased to the 10 by the 10 orders of magnitude, basically. So that is why. So the lesson is that actually the other thing to note is that if your samples were sampled, if your samples had zero noise at all, like if there was no noise at all, like if it stuck to the orange line perfectly, then there probably would have been no problem. But usually your samples do contain noise anyhow. Like there are just unavoidable observation noise. Like, you know, if you're sampling from, if you're collecting data from sensors or wherever, like anywhere, the noise is always there. So, and if your model power is too big, then it'll be very sensitive to all the small noises, all the small, like in the small tweaks in the training samples, and it'll overfit like this. So you don't want to do that. So here we call this underfitting. Your model is too weak to properly fit to the training samples. Here is overfitting. It is just, you know, it is fitting too well to the training samples, and then it's just not generalizing well to the true test samples. So how do we know that the model is overfitting or underfitting? So this is pretty easy, actually, because as you increase your model capacity, like you start from the like a first order polynomial function here, second order polynomial function here, all the way to like fourth order polynomial function here, and then this like 15th order polynomial function here. Then as you increase, sooner or later, your test performance would be decreasing while your training performance still increases, because as you increase your model capacity, you can exactly fit the training samples. Like here, you can exactly fit the training samples and incur 0% training MSE. So your training loss would go down and down and down as you increase your model performance and model capacity. But then your test performance would at some point go back to the increasing mode. So you want to find the right balance of your model capacity. So doing too well on training data doesn't always lead to good test performance. It doesn't generalize, right? So in deep learning, the reason that we have a validation set is because instead of using test set, we can use a validation set, because you should never ever use test set while training. So you can use validation set instead, and then as you increase your model parameter, or as you keep training your SGD iteration, you can see when validation performance starts to decrease or validation error start increasing, then that is when you stop your training process. Right, so overfitting, underfitting, just another depiction. Like you can, the underfitting, overfitting, this concept can be applicable to any learning. Like it could be applicable to regression, classification. Not sure why. I mean, setting a deep learning as a separate category is probably not a good idea. But you can see what happens with regression and classification. If your model, if your training distribution is quadratic, and you would like to use a second order polynomial function, but when you use first order, then it is underfitting. If you use a very high order polynomial function, then it will be hitting all the noisy samples in the training samples, and then it would have a very squiggly line like this, which is not going to generalize. Same with classification. If you have a sample like this, and the decision boundary should look like this instead, like this. So this would be the perfect example. Here would be an ideal situation. If you use like a very weak classifier, then it would draw a decision boundary like this, and all these points here are misclassified. Like here is all misclassified. But if you use a too powerful classifier, then it would react to all the small noisy, noisy samples like this and here. So it would have a very, like on the surface, it would be a perfect classification of the training samples. But then if you, in the test case, in the test scenario, like another red dot would be here, like another red dot would be like here, red dots could be here, and then a lot of blue dots could be here, and then these would be misclassification, like here. These are all misclassification in the test phase. So it would incur a very high test error. So you don't want to overshoot. So what can we do when we see underfitting or overfitting? These are some of the easy remedies. If you are underfitting, if your model is underfitting, you can complexify it. So you can basically increase the capacity of the model, use higher order polynomial function, or maybe put some more layers in your transformers, something like that. Or you can add more features. You can start adding more information to correctly classify or train longer, optimize longer. Overfitting. So underfitting is actually usually it's easier to overcome, because you can just simply use a higher, like a more powerful function. But the overfitting is actually the problem, because when you're overfitting, the ideal solution is getting more training data. This is always a good idea. If your model is overfitting, get more training data. That is always a good solution. But usually it's not very easy to do so, because in supervised learning, you usually need hand annotation. Human labor is involved in creating a data set. So this is not very easy to do. So what you do is instead you use a reasonably powerful model with some regularization. I guess regularization is on the next page. So we will talk about the regularization. Before we move on to that, curse of dimensionality. So these are all very basic concepts, like overfitting, underfitting, curse of dimensionality. This is like the go-to interview questions when you apply for like ML engineering positions in IT companies. So curse of dimensionality, as I said, when underfitting, you can add more features. So this is one solution, but you don't want to add too many features at once, because there's something called curse of dimensionality. So what this means is that as you linearly increase the number of your features, so linear increase in number of features, the model requires exponential increase in the number of data to fill the space. So for example, if you use only one feature to determine whether something is like dog or no dog, or in this case, like here, I guess this could be like it could be a dog or no dog in this case as well. So if you use only one feature at a time, then you can just simply need some number of training samples to determine, any sample that has the feature value lower than here would be all dog, and any samples that have a feature value higher than here would be no dog. Like this would be a very straightforward example. But if you start adding more features, like if you start using two features, then you need to see a combination of those two to determine the decision boundary. Here, decision boundary is like this, but in here, decision boundary needs to be two-dimensional. So you need to see more data. Like what happens when your feature A and feature B, what happens when your feature A has value this? Sorry, again, I'm actually confusing. So what happens when your samples first feature value is like this and second feature is value like this? Or what happens when your sample has like very high value in feature A, another very low value in feature B, or vice versa? Or maybe those two features are all high, or maybe those features are both low. So it could be like here, and you need to check all the cases to draw a decision boundary. And things get worse when you go three-dimensional. If you start using three features, then you need to see all three combinations. Like what happens when your ABC is all high, all low, high, low, low, high, low. Like, basically that is why you need exponential number of data, exponential increase in your number of data in order to fill the space and then properly draw a decision boundary. So you don't want to you don't want to ignorantly increase the number of features so as to get a better performance. It's always a bad idea. And this still plays some role in modern deep learning, especially in NLP, because NLP, your words become the number of words in the dictionary becomes the number of features in your data set. So you don't want to use too many words. So that is why people use like subword encoding of subword vocabulary of 3,000, 30,000, or 50,000, or 10,000. Right. So far, so good. Right. This has actually a tie to linear systems, when you have like a linear equations with 1, 2, 3, 4, 5 variables, 1, 2, 3, 4. Like if the number of linear equations with the number is the same as the number of variables, then you have like one solution. If you have a full rank matrix, I'm just talking about linear algebra. But if you have larger number of variables compared to the number of linear equations, then there can be many solutions. And that is exactly when there are too many variables, too many features. So you don't want to use too many features. Right, moving on. So regularization. So regularization was one of the easier practical solutions to when your model is overfitting. So regularization is basically restricting the freedom of your model. So even if, before we begin, so when your model behaves like this, your 15th order polynomial function behaves like this, like in a very, very squiggly manner with a very, very rapid change. Like even if you move your x very slightly, it suddenly changes from here to here to here, right? So that sudden movement is only possible because the coefficients or the weights have a very high magnitude. So if your polynomial function's coefficients have a very high magnitude like this, then your function would behave in a very a crazy manner like this. And you don't want this to happen. You want your model to be you want your model to show a more or less like a smoother behavior. So that is why you use regularization. So for example, you can use L2 regularization, which is basically adding one additional term to your loss function. And basically what this term is that you consider all these W's as a vector. So it's a multidimensional 15th dimensional vector, and you want your vectors, weight vectors, norm, squared norm, basically magnitude, to be as small as possible while minimizing your loss, because you want to minimize these both at the same time. So you want to minimize your loss, you want to minimize the norm of your weight vector at the same time. So basically what you're doing is you're restricting the freedom. So you don't want to see values like these, like high values like this. You want your W to be like 2, -1, -3, something like in a more well-tamed manner, so that it becomes more smoother like this. So basically what you're doing is you're downsizing the hypothesis space. So L2 regularization looks like this. There's another thing called L1 regularization, which is basically using first norm, one norm to as an additional function, as an additional loss function here, and there's one norm here, and depending on which regularization you use, whether you use L2, whether you use L1, the solution that you reach, or the final parameter that you obtain from the optimization process will be slightly different. Like, if you use L1 regularization, your parameters will be, your final solution would be sparse. If you use L2 regularization, your final solution would not be sparse. So depending on what kind of solution that you want to obtain, you should use different types of regularization. I mean, we won't go into detail about this though. Right. Moving on. So I guess this is the last part in our last material in our class today. Some of the popular classifiers. So far, any question? Because the rest is just introducing some popular classifiers and clustering algorithms and whatnot. So this would be our end material. Any questions so far up to regularization? So we talked about optimization, stochastic gradient descent, evaluating the function, and then overfitting, underfitting, cursive dimensionality, regularization. All these are very, very very core concept of machine learning, basically. And we would be stumbling upon these. We'll come across these concepts very often as we move forward into the deep learning study and deep learning, writing codes in PyTorch and introducing new concepts of deep learning models. We will be revisiting these concepts, but I won't be explaining what they are. So you should be very familiar with what they are. N-fold cross-validation unnecessary, that is only when it comes to modern deep learning with a lot of data. 그러니까 이제 그 한국말로 얘기하자면 N-fold cross-validation 하는 이유가 애초에 데이터셋이 적으면은 100개밖에 안 돼요, 샘플이. 그러면 그 100개를 이제 뭐 8대 1대1로 나눈다 그러면 이제 뭐 80대 10대 10으로 해서 이제 테스트 샘플이 10개밖에 안 되잖아요. 테스트 샘플이 10개면은 그 10개를 믿을 수가 없단 말이에요. 그게 운이 나빠가지고 아주 어려운 애들만 들어가거나 아주 쉬운 애들만 들어갈 수 있기 때문에 그런 애를 가지고 테스트를 쟀더니 엄청 잘 나오더라, 엄청 못 나오더라 그러면은 그게 무슨 의미가 있겠습니까? 그러니까 이제 테스트 셋이 충분히 커야지 테스트 셋으로서의 의미를 이제 가지는데 내가 이제 샘플이 100개밖에 없으면 그런 상황이 가질 수 있기 때문에 일부러 그럴 때 이제 nfold를 하는 거예요. 그때 이제 10fold를 하면은 10번의 테스트 셋이 나올 거잖아요. 그럼 이제 테스트 셋을 10번을 가지고 재면은 잰다는 건 뭘 재는 거예요? 모델의 퍼포먼스를 재보는 거잖아요. 그러니까 이제 결국은 에스티메이션을 하는 거잖아요. 그래서 이제 통계 때 배웠던 시간을 생각해 보면 통계 때 뭔가를 에스티메이션 할 때는 샘플 수가 많을수록 베리언스가 확 줄어들잖아요. 그런 것처럼 우리는 지금 모델 퍼포먼스를 트루 모델 퍼포먼스를 에스티메이션 하고 싶은 건데 테스트셋을 이용해서 그때 테스트셋을 여러 개 쓰면은 엔포스 크로스 밸리데이션 통해서 테스트셋을 여러 개 쓰면은 파이널 모델 퍼포먼스 에스티메이션의 베리언스가 굉장히 낮아지겠죠. 그러면서 이제 트루 모델 퍼포먼스를 얻을 수가 있다 이런 얘기입니다. 근데 만약에 애초에 우리가 데이터셋이 뭐 1조 개가 있어요. 그러면은 1조 개를 8대 1로 나누면은 몇 개예요? 9천억, 1000억, 1000억이잖아요. 1000억 개의 테스트셋이 있으면은 이미 너무 많아가지고 이 스태티스티컬 파워가 굉장히 세기 때문에 굳이 이런 엔폴드를 할 필요가 없다는 얘기예요. 그러니까 1000억 개의 테스트셋은 이미 레프레젠테이션 파워를 가지고 있기 때문에 거기에 대해서 테스트 한 번만 해도 모델의 트루 퍼포먼스를 충분히 에스티메이트 할 수 있다입니다. 혹시 이해가 되시나요? 제 설명 이해가 되셨나요? Alright, hopefully that works. Right, so the end material, some popular classifiers that we won't get into. Actually, no. Logistic regression, the third class next Tuesday, we will start with logistic regression and then we'll build upon logistic regression towards multi-layer perceptrons and then how to code that in PyTorch. So we'll be studying logistic regression in a bit more detail next class, so we're going to skip past this. But basically, it's a probabilistic model. Starting from probability, we turn that into an odds, and then we put a log function in front of it to make it into logit, and then that's how you get logistic regression. Support vector machines came proposed back in '95, and then was very popular. It was a go-to method in the mid 2000s. Still, like the spirit still lives in the hinge loss form of hinge loss, and the objective is to maximize the distance or the margin between your decision boundary and the closest samples to the decision boundary. And it's called a margin. So you want to maximize the margin. And maximizing margin is directly helps your model achieve generalization performance. We won't go into detail, but training is usually done by like constrained optimization using KKT theorem, but we won't go into detail. Decision trees are another family of popular classifiers. You train via a CART algorithm, and it looks like this basically. You have a number of features that you want. You have a feature vector, and then you put that into an algorithm, and then the algorithm will use features one at a time to build a decision tree like this. Like it's like an algorithm basically. Ensembles are actually like a philosophy of training a classifier. It's using a multiple simple functions, like easy, like low power or low capacity functions, multiple of them, and then ensembling them to ultimately derive a very powerful function, powerful classifier, powerful regression function. And there are two schools of doing ensembling, which is one is bagging, another is boosting. And bagging is actually training multiple classifiers on different subset of data. You have a train like a mother that you have a whole training data, and then what you do is you sample subset of them like maybe 90% at a time. Like you can have multiple 90% training samples, and then you train multiple classifiers based on them, and then you average them, or you do a voting or whatever. Just do an ensemble. That is one way to do it. Another way to do it is to use a different subset of features instead. If your data set consists of 100 features, maybe you use 90 features at a time, and then you train multiple classifiers. And this is actually the spirit of random forest. Boosting is it's like a chain of classifiers. It's here in different subset of data, different subset of features. They're all used to train, like, the same level, like multiple classifiers that behave in the same, that are all on the same level. But in boosting, it's kind of hierarchical, because you employ a weak, like chain of weak learners, or series of weak functions to classify, to solve the problem in a small, like bits and bits of manner. You train your model to do a classification, and then you get a bunch of things wrong because you're using a weak learner, and then you send them to the next level, and then you train another function to do another classification, and then you get the subset of them right, but you still get a bunch of them wrong, and then you send it to the next level, and then until you're satisfied. So it's a very, very powerful method to obtain a high-performing model. And usually when you do like a hackathon, or like a competition, or like a leaderboard, usually the prize winners, like the first places, or like a high-ranking competitors, usually resort to boosting or bagging, some form of ensemble, because it's a very powerful method to increase your model performance. Right, moving on, some popular clustering method. K-means clustering. Well, I mean, we don't have a lot of time, so we won't be able to go into detail. It's basically you predetermine the number of clusters that you assume there to be in your data set, and then you update your centroid, which is like the center of your cluster, or the representative of each cluster. You update your centroid, and then you reassign the samples to the centroid, and then you update the centroid, you reassign, then you update centroid. It's like basically running this for loop over and over again until you're satisfied, until the assignment doesn't change further. You can actually generalize it into a probabilistic manner. K-means clustering is purely geometric, but you can actually put more probabilistic spin on it, and assume that each cluster is Gaussian distribution, and then you assume that a sample is probabilistically belong to each cluster, like like a certain sample, like sample here has a 20% chance, 30% chance of being in cluster 1, 10% chance of being in cluster 2, like almost 0% chance of being in cluster 3, something like that. But here in K-means clustering, one sample can only belong to one cluster at a time. So this is like a hard clustering, and this is soft clustering. And you use expectation maximization, EM algorithm, to train your mixture of Gaussian clustering. Yeah, all these are like, all these models are worthy of studying one at a time in a very detailed manner. But since we don't have a lot of time, we have whole other deep learning models to study this course, so we won't be able to delve deep into the nature or the properties of these different algorithms. So if you're interested, please study on your own time. I mean, these are some of them are still used very, very frequently these days, so it's worth knowing them. All right, I think this is it. So yeah, 10:12. So sorry about the running overboard. Any question before we end? I'll be able to answer maybe one question. Or I'm going to wait 5 seconds before I end. Okay, so no question. But if you do, you can always post them on Classroom. And please recap this material very carefully, because I won't be explaining them probably ever again after this class. Like from now on, it's all deep learning, like all like autoencoder, GAN, VAEs, all RNN, CNN. So we won't have the time to revisit the concepts here. All right, thank you very much, guys. I'll see you guys this Thursday. By the way, this Thursday we'll be studying scikit-learn, which is a Python library that has all these concepts in one library. All these concepts that we studied today, they're all in scikit-learn. All right,
감사합니다.
네, 감사합니다.